So that's there. As the key thing that I want to cover today that is coming up, is going to be important soon, is our learning outcomes exam. It's the only comprehensive test in the whole course. And I'm not saying that it's complicated, but there's some topics that it covers that it's covering everything within the course to a degree. It just means that some things that we talked about back in August and September might be distant memory. So that's what can make it throw you a little bit. And then just the way that some of the stuff is being asked, I guess. So I'm going to point out there is a study guide in week 14 for you to go and use to prepare. So that's important that you spend a little time with it. I'm going to go through that study guide too in just a moment. I should bring up is our guys. So the learning outcomes test is what I want to kind of focus on here. So I'm just trying to bring us down to where we're at here. I just feel like you need to have this information first as we're coming up to a couple of other deadlines, and then I can still have time to catch up on the other material that we're dealing with. So let's see. Let me share first our Canvas course for a moment, just to show where we're at. When you come up here, we had exam number 3, and there's still some people that haven't done it, and I've left it open for people because I'm, really want people to succeed in this course. And so I'm I know if you have done it and you did well, then that's great. But it's a tougher test, and I still haven't finished looking at that test. I may still do some adjustment for a curve of some sort on that test. But some people did extremely well, so it's not completely just a curve-worthy test, but it is probably the toughest of the bunch. This next test, our last test, exam number 4, deals with structural steel, so that's week 12, and steel framing, and that's the recording that's missing here, so I'll have to go back to that from last week. I had a couple of people here, but something went wrong with the recording, and I'm just going to have to redo it. So I'll do that. But in the meantime, then we're dealing with roofing, which is chapter 11 and 12 last week, and we're kind of officially moving into week 13 right now, where we're dealing with roofing and more roofing. And so, yes, that's the big stuff. But we have another week after Thanksgiving, so I can still continue dealing with that. But meanwhile, what's opening up during Thanksgiving week and continuing on is this learning outcomes exam and your essay. You've got a research essay that's due. So those are a double whammy coming up here right now. I'll basically due on the Wednesday after we get back, but oops, okay, I double clicked on something here. So let me bring us back. Yes, it worked pretty good. I collapsed something is what happened. Then I clicked on something else in the aftermath. Anyways, so I'm focusing on the week 14 material. I'll come back to the week 13 material because we do have a little bit more time than that, but it's going to open up. Let me just see. I don't have that in my mind here. So let me look. Learning outcomes. Well, that's week 14. If I click on the test for a moment, yes, it says due November 30th, but which is a Wednesday after we get back from Thanksgiving. But it's going to open up this coming Wednesday. I think it's Wednesday. I don't know exactly. Sometime Thanksgiving week. And so then it suddenly be available. I want to make sure I've covered that material because of that. And meanwhile, if I back out of there, we've got within that same week, you can get a chance, Canvas a chance, you've got this research essay. So you got research essay instructions here. And then if you'll still see research instructions, if you click on the research essay assignment itself where it says upload here, When you click on that, it describes, yes, you're supposed to have 1,200 words, which is about 4 pages double spaced if it's in 12-point font, plus a bibliography. So your sources of information. So, and you should have really 3 sources of information. Now you could use the building codes as part of that. You can quote building codes. That'll make me happy. There's nothing wrong with doing that. But you, depending on what you're talking about, you can talk about any construction related topic that we've kind of gone through. So I've kind of given a list, but it doesn't mean it's comprehensive. These aren't the only ones you can pick, but I'm trying to give you some ideas. I've had students, oftentimes they want to write about what they're interested in, and that's fine for you to do that. But you can branch out from there. I mean, I've touched on environmentally sound or sustainable practices in construction, and you can certainly focus on that if you want, or you can, other green construction things, so there's that, but you could focus on a bigger topic or a smaller topic. Then, you can focus on foundations or a particular kind of foundation, or you could talk about framing up a house or a special kind of framing. There's different energy efficient techniques for framing that put less wood in the wall, so you have more room for insulation and stuff. Or you can focus on concrete. That's a favorite topic for me. There's a lot of different kinds of areas you could specialize in concrete, and just the concrete technology, or placing and finishing or forming concrete, or you can focus on the precast concrete. You just want to make sure you pick a topic that's going to be small enough for you to cover in 1,200 words, big enough for you to cover in 1,200 words, and I want it to be your work. If I go, it's a fun technique, fun, maybe not fun for you, but fun for me when I look and cut and paste some words that just seem a little bit too professional and put them into into Google. You can paste that stuff and you'll pop up in the book or the article. It's stuff is extremely searchable. So that's really what some of this special software that looks for plagiarism does. But I want you to use your own words and use your own thoughts in here. I'm not after expecting Pulitzer Prize winning essays. I want you to write with your own words in here, and not try to just cut and paste stuff. And you're trying to and then down here at the bottom, when you're looking at the actual assignment, if I was in student view, let me do that. Go to student view for a moment. There, it says start assignment. Well, that's not where you start the assignment. This is where you finish the assignment by uploading it. You click on here to upload your file. The thing is, I can't, isn't the right word. Canvas cannot read this proprietary format that Apple makes called Pages. So that's not one of the file format. It has to be either a Word file. The old style file would be doc, and then docx would be the modern kind. You can use a PDF file. I've even put in a couple of basic rich text file as a very old format. And then if you've got a Chromebook, then you might use Open Document Text, ODT file extension. So that's all fine to use those kinds of files. But Pages, for me to open that, I'd have to go and send it to some mysterious dark website in order to convert it. And you can do that. I've seen and I've worked with Pages. You just got to be smart enough to go, and when you click Save As to finally make your final file that you're going to submit, you save as, and you can save it as a doc file or a docx file or even a PDF file. You just got to do that last step before you send me, don't send me a Pages file. I'll just tell you got to go and try again, to submit it. Because I'm not going to be able to read that file. It's what happens because Macintosh or Apple, they get so secretive with all their stuff, so they don't make it available so anybody else can read those files. It's their own fault. And these other systems are open file systems that are meant so that systems like Canvas can read them. Otherwise, they'd have to go buy some software from Apple for an extraordinarily high amount of money, I'm sure. Anyways, I digress. The point here is that you want to make sure that you follow this rubric down here. I've got a rubric, and this is what I'll be using to grade right here. The top section, this bottom section is not really part of it. That's part of our accreditation. I needed to have something in there for that. But yeah, effort. So if you're sending me a 600 word file instead of a 1200 word essay, well, that's going to be lower in the effort. That might lose 15 points, Content, you got to make sure you give me accurate information and using the vocabulary of construction. Not calling it a thingy or a doohickey, use what it's called. That's part of your research to make sure you're using the right terminology. Grammar, spelling, punctuation, basic stuff, that's worth about 20 points. And so, yeah, if you're not even using spell check, even Pages has spell check. And by the way, you can always, if you got a program that doesn't have spell check or however you're using it, you can always subscribe or set up to Grammarly for the free version of Grammarly, and it'll do all kinds of spell check and more for you on any program that you've got. And then documentation. If you don't have a bibliography, that's going to lose 20%. The other thing is, this is the one thing that I will be taking points off of in here if it's late. And so after the due date, I'll still accept it. It's worth too much. It's worth 10% of your grade. So to not submit an essay is to drop your grade by a whole letter grade. If you had a C, you'll have a D for not submitting this essay. So I can't grade it. I'll try to grade it kindly, but I can't grade it kindly if you don't submit something. So you got to submit something, that's for certain. But anyway, so that's something to keep you off the streets during Thanksgiving holiday. Okay, you got more time than that, but because it'll be due the Wednesday after we get back. So you got some time. But anyways, that's all part of that week 14. And then week 15 is really the final exam week. So if I go back to modules, I'm in the student view, but still it should work. Scroll down, I'm scrolling, and week 15, and that's final exam week. Now, our final exam week in this course is going to end on the Thursday during final exam week, not the Saturday. Yes, the Saturday is there for the last causes, but I have other responsibilities. I've got to grade stuff and submit and do all kinds of other things besides grading. And so the Thursday of final exam week, that's the 8th of December, that's when absolutely everything in this course is due in all ways, shapes, and forms. And so just understand that that we're coming to the end. And so, I can only delay things so much. And at some point I got to submit grades, and same thing with the other teachers. So the deadlines cannot be extended, is what happens here. So, okay, that's enough nagging. I'm preaching to the choir here. The ones that are here in Zoom right now are not the ones I'm worried about here. Okay, so I'll leave that view here for a sec, but I also need to unshare this so I can go back to the key thing that I wanted to focus on was the learning outcomes test. I guess I should have pointed it out, but in week 14, you'll see that it says study guide in week 14. It said right above the learning outcomes test, it says the study guide for learning outcomes exam. And if you're in my safety class, you got the same kind of a file, but again, for the safety class, it's a little different. But that's what we want to look through first here. Okay, so I'm going to bring that up. Oh boy. Everything changed on this thing. There must have been some major update. That's not normal for. Sure, I get that off of here. Something got set hinky in here within. So let's see, under slideshow, not automatic, primary monitor. Okay. So now we got it on the right screen anyways. Yeah, it must have been a Microsoft update of some kind. Okay, so here we are, so I can go share it. Okay, blow by blow, but here I'm finally getting ready to share that screen. Okay, so it should be popping up now. So I got this jazzy looking page that I put in here, but learning outcomes is what we're talking about in here, and that learning outcomes test. And so here we go. So in here, it's a PowerPoint presentation, but I've converted it into a PDF. maybe I should try to reformat it for you in a different way. I'll think about that here, but that's the way the study guide is right now. And this looks just like this, except that instead of being a PowerPoint file, you can use PDF software to view it. So there are 5 learning outcomes that are part of this course that are being measured. And so one is about the use of, understanding the proper use of materials, or the proper properties of materials, and that kind of stuff. And so there's stuff here about proper materials. I think I've got a couple of pages, 2 pages dealing with that. So each one of these bullets that you see could be turned into a test question near you. I mean, think about that. So kind of look at these things with a critical eye. So look at the first statement. It says foundations are primarily made of concrete. Wood foundations are problematic. Okay, I put that in brackets. So I guess I could ask you, what are foundations normally made of? Okay, that wouldn't be too complicated of a question, but it could be there, That's a good example of where this thing could be going. So think in terms of that when you're reading these statements on here, because it's really statements that could be turned into test questions. So think about it in those terms. So yeah, of course, almost all foundations are made of concrete. It's what makes sense to have in direct contact with soil. But because of that, concrete can soak up moisture. And so any wood that is in direct contact with concrete has to be protected in some way. And typically in modern times, we use pressure-treated lumber for the first piece of wood that is in contact with concrete. And actually, it's even better if it's sitting on a flashing or membrane of some kind, so it's still isolated. And then you don't build the whole house out of pressure-treated lumber. That's not a good idea, because it's not kiln dried typically when you get this stuff. Most of it is not. It's soggy, it's going to shrink, it would be a problem. But anyways, I digress beyond. Okay, the next second bullet on here, heavy timber performs better than unprotected structural steel in a fire. And so we talked about that in the chapter 4 in the heavy timber chapter. And we also talking about that right now. Of course, now that my video is messed up, you're not seeing that, but it's one of the first things we talk about with structural steel in chapter 11. So on both sides, we're looking at it from both directions. But yeah, structural steel is horrible in a fire. It starts to lose its significant strength around 500 or 600 degrees, and it's lost 90% of its strength at 800 degrees, and it's lost all of its strength at 1500 degrees. And most fires are 1500 degree fires. And so that's a very, very common temperature to be dealing with things at the actual fire level. So yes, heavy timber is going to have a certain burn rate, and that's why it performs so much better, because it's so heavy that it takes time to burn through even a little bit of that big chunk of wood. And so that's why it works so much better. But if you're dealing with something much more slender, like a wood I-joist, which is kind of a manufactured, engineered I-beam out of wood, it's very slender, a lot of surface area for just a little bit of wood. Oh, it's horrible. They are the least fire resistant of all framing members of wood framing members. So wood I-joist would be the opposite of heavy timber as far as heavy, that goes. Now, that doesn't mean other engineered lumber is going to be a problem. Heavy timber could be glulam beams, and though that's considered heavy timber and that's engineered. LVL and PSL, parallel strand lumber and laminated veneer lumber, that's engineered lumber, and they fare pretty darn well in a fire too, especially depending on how massive they are. So remember, heavy timber by any definition is at least considered heavy. It's considered heavy timber if it's 5.5 inches in its least dimension, or in some definitions more than 5.5. So that's in the smaller of the two dimensions, in the way that 2x4 is 2 inches by 4 inches is really 1.5 inches by 3.5. So 5.5 inches is the actual minimal size for heavy timber. 6 inches would be the nominal size, the rounded up size. Okay, so that's looking at this first page. The next page, still dealing with the same thing, same category. So you're basically going to have about 5 questions under each category. So we're still under the first category, proper materials. Green lumber shrinks more across its grain than along its length. If you remember back in chapter 3, we were talking about the circumference of a log and across the grain in any way across the grain. So across the grain, radial shrinkage or tangential shrinkage are both really across the grain shrinkage, and that's a bigger factor for either of those compared to longitudinal shrinkage along the length of the log or along the length of the wood. And so that's all we're saying here. But you didn't need to have those terms to understand. This is just the basic factoid here. Yeah, green lumber is going to shrink. It's going to shrink a lot more across this grain than it will along its length. That means a log in a log cabin is going to shrink a lot more as a percentage across the diameter of its log. You can get a 10-foot tall log cabin, a green lumber, it's going to become a 9-foot tall log cabin by the time it's reached equilibrium moisture content. Okay, the next bullet, it says, for a given beam depth, which is the height of the I-beam, for instance, or, but we call it depth because when you're standing on the beam or standing on the floor system that the beam is part of, it's like the depth of the floor, how, below your feet. But anyways, for the given beam depth, steel beams can span further distances and or carry greater loads than wood beams for the given depth. So that's a truism that's always true. And so what happens is if you need to take down a load-bearing wall and make a great room, a big room out of two rooms, and you need to then replace that load-bearing wall with a beam. And if you want that beam to be inside the ceiling and not stick out into the room, have it hidden, and then one way to do that is to switch to steel, because maybe the wood beam would be too massive. And you might not even have proper head clearance. It all depends on what kind of loads and how big that beam has to be. Well, the way to solve that is to move to steel beams. So again, as we're saying here, for a given beam depth, the steel beam can span a greater distance, carry heavier loads, either way, than a wood beam would. Okay, one other thing about materials, a little factoid I want you to remember, and that could show up in a test question near you too, is talking about aluminum flashing. You can have aluminum flashing, there's nothing wrong with it, but you cannot have aluminum flashing in a case where it can be touching or embedding with concrete or masonry. So the whole point here is aluminum reacts with concrete, with Portland cement, with mortar and masonry and brick and concrete masonry. So aluminum is a big no-no. You don't when we have flashing around a chimney, for instance, you don't, the best way to get flashing to work best is to have some flashing, some counter flashing that is actually sticking into a saw cut in the side of the chimney so that you caulk it into place. But you don't use aluminum flashing. You can have galvanized flashing, you could have copper flashing, stainless steel flashing, you could have, heck, you can probably even have plastic flashing if you find some fancy plastic flashing that's durable, possibly, maybe with some of those fancy plastics, possible, but never aluminum. And that means no aluminum in fasteners and flashing, touching concrete or masonry. That's what we're getting at. Okay, now we're going to the next topic of the 5 topics. So topic number 2 here, talking about lumber and panels, and we're talking about different factoids and things about materials. So we're talking about the materials themselves in this whole test. We're talking about, in this whole course, we're dealing with materials, various materials. We're also dealing with materials and methods. So the methods that we use them, and so some of it has to do with how they're fastened together or used. And sometimes it has to do with the tools and equipment used to connect these things to each other, to other things. The most critical thing is when you're switching from one kind of material to another. That's where things can get tricky. So anyways, with that in mind, we're talking about, first of all, on this page, structural wood panels. Well, that's a fancy name for plywood. Well, it's more than just plywood, but plywood is part of it. So a big part of when we talk about a structural wood panel, it's just an unnecessary word with extra words and stuff. We're talking about plywood, but the reason it exists is because because nowadays there's a lot of stuff we use that's really a plywood substitute, like OSB. Or OSB is the wafer chip board that you see on the side of a house when it's being built. Those plywood-like sheets are called oriented strand boards. So that's what OSB stands for. And that's a structural wood panel too. And if you're using some kind of fancy thick particle board for your subfloor, which might work pretty good because it's such solid material, you could get like maybe 2 1/8, 2 1/4 inch thick particle board. Boy, that's heavy stuff. And that would not be called plywood because there's no veneers of plywood glued together. Instead, but it is a structural wood panel. So it's a bigger, broader category than just plywood. But all plywood would be considered a structural wood panel too, or in that category. Okay, so what are the properties of structural wood panels? That's what we're looking at, because we're looking at the pros and cons or the properties in here. So I got 1, 2, 3, 4 properties that I want you to make sure you got straight. They might all show up in one question. And maybe what you're looking for in the question might be for what's not true or something. Okay, but let's look here. It says, okay, what about structural wood panels? They're nearly equal in strength in both principal directions. And that's different from a solid wood board where all the wood grains are going in the same direction, the way the tree was growing. If you have a solid 2x4, it's only strong in one way. Left and right, if you're holding a board horizontally in front of you, I guess you say, but that's considered one direction, compared to a sheet of plywood where you got every other veneer that's glued together is rotated 90 degrees from the other one below it. So as you're stacking them up and gluing those veneers together, you've got wood grain strands going in both principal directions, which makes it strong. And if you're dealing with oriented strand board, the wood chips are randomly placed so that the fibers are all going in random directions. So yes, it's going to be strong in both directions as they glue all those little wafer chips together, those little chips, strands and stuff. Okay, that's the first one. Nearly equal strength in both directions. Next bullet point there, a little plus sign, it says it's a more efficient use of forest resources than solid wood boards. You get to all these old houses that are, I don't know, 70 years, 80 years, 100 years old. There's no plywood in those things. They kind of hadn't figured out how to make plywood until the 50s. So yeah, if you've got a house that was built in the 40s, or older, unless there's been remodeling done, you're not going to find any plywood anywhere. And there are a whole bunch of solid wood boards that they used. It meant there was a lot more wood used to build that. And back then they had great big old trees they could cut the stuff out of. Now we've used up most of those. So we can make plywood panels or structural wood panels of various kinds from relatively young wood, so we can grow it like a crop. So it's a more efficient use of forest resources than solid boards. Okay, so that's one thing. Next point, the structural wood panels require less labor to install than solid wood boards. You can put up a 4x8 sheet of plywood pretty quickly. That's 32 square feet. Whereas other boards you're going to put up, you're not going to be putting so many square feet up at a time. And so that's where the efficiency comes in. The last point on this page, structural wood panels, the shrinking, swelling, splitting, and checking of the boards are reduced in panels compared to solid wood boards. The knot holes can be removed or avoided. They can be filled in various ways. There's a lot of neat tricks with plywood, and even more with structural wood panels like OSB and such, where you can make a very perfect piece of wood that doesn't have any flaws, or at least not, depending what grade of plywood you're dealing with, there might be flaws that are not a problem. But whereas with solid wood, you've got to keep sorting and figuring out, we can't use that board because of this issue and that issue. So yeah, all of these things are true. So just make sure you kind of have them. I'm spending way more time than you would have to if you're just kind of looking through this and acknowledging these factoids. We're still looking at lumber and panels here on this page. And so now we're looking not so much on the panels, but on engineered lumber. And so first of all, glulam. So large wood beams are usually glulam these days because there are, what are the reasons? And those three reasons right there. There are fewer large old growth teas. Well, that's supposed to be trees. Unfortunately, I can't change it. Whenever I see that, I'm in the middle of it. But yeah, it's supposed to be trees available. They're gone. I mean, you know that there's just, you don't find trees that are 20 feet in diameter anymore, and, and even 10 feet in diameter. They're just not around. Next point, laminated beams can be made to an exact size and shape. You can have curved or arched wood when they're glue lam, because they can be custom made into that curve. You can't do that with any other kind of lumber. You can cut it and waste some lumber by kind of making a curve out of piece of a wood, but that's only at a small size now could you do that. So it just doesn't happen for large wood, heavy girders, you know. So most of the heavy timber nowadays is glue lam, for that matter, because of that problem. And they can be curved. Okay, pound for pound, a laminated beam can be made stronger than a solid wood beam or a sawn beam, as I've got it written here. Because in laminated beams, which is glue lam beams, you can actually embed fiberglass strands in between the wood pieces, so that you actually create kind of like the same principle as rebar does in concrete. You can add reinforcing into a glue lam beam because you're constructing the beam from scratch, you know, and so they do. It sometimes means there's a top and a bottom of that beam, even if it doesn't otherwise seem like there would be, because maybe the fiberglass strands are only in the bottom area where it's needed the most. Okay, so that's another page down. Still dealing with structural wood panels, and here we're looking completely at engineered lumber, the first bullet and sub bullets. So I want you to know the names of the different types of, okay, here's a mouthful, structural composite lumber. Okay, so I'm not going to have, I'll have the term, this is also called engineered lumber, and you see that in brackets, and I'll have that term in there on the test too. So, but you know, just so you kind of know, when you hear that term structural composite lumber, that's a fancy name for engineered lumber. I think most people use engineered lumber, but I do want you to know that term. So these are the three that I've talked about a lot, and that's laminated veneer lumber, LVL. That's where you got veneers of plywood glued together like plywood, except that all the veneered strips are going in the same direction to make a beam, a heavy duty beam. Parallel strand lumber, where PSL, so LVL or PSL. So parallel strand lumber is PSL. And that's where you've got strips of wood, little strands of wood that are all glued together randomly, all pointing the same direction, you know, so that you can glue together a beam made up of sticks of wood, basically. And that is probably where the future is going, because that's the most efficient use of lumber. They're very heavy because there's a lot of glue in them. But anyways, and then laminated strand lumber, or LSL, that's the least important of the bunch. And that's going to be basically looking like OSB, oriented strand board, except it's made into a beam form, into a beam. It's not going to be able to span as far, but it still can be made into lumber or a beam of sorts sometimes, for headers, maybe, for that aren't, as long as they're not spanning too far. Now down below that, I point out about oriented strand board. I kind of fit it there because I had some space for it, I guess. But remember what OSB stands for. And so I've got it written here again, oriented strand board. And so this is, the individual strands are oriented. That doesn't mean somebody is individually placing and orienting these things. They have a machine that's randomly spraying them out into a form with glue and making the sheet of plywood. So this is a panel. Now, what we said before on this other page back here where we talked about structural wood panels, and I mentioned OSB in brackets, but here I'm spelling it out more. So what is it? It's a panel that is often used as wall and roof sheathing. So that's probably what we're going to be asking here, is what do you use these panels for? Well, it's used a lot on walls of houses, on the exterior walls, not interior. I mean, not for finished work. It's a structural panel. And so it's used on the outside as sheathing, on the outside, wall sheathing, and it can be used up on the roof as roof sheathing. That's actually nailed to the rafters on the top or the trusses, you know, and this is mostly residential construction, this would be done. But if it was used in commercial, then it would have to be encased in a fireproofing material like exterior grade drywall or something. Okay, enough talking. Let's move to the next page. And so the next page, we're going into a new a third category dealing with of question, another 5 questions that could be in here. And yes, some of this stuff is a little headier. So I just want you really to know more about the key words in here, and there's more stuff than you might need in here. But so we can talk about moisture barriers. There's a vapor retarder is a type of a barrier of sorts, and then air barrier. So a moisture barrier keeps liquid water it resists the migration of liquid water. So that's what a moisture barrier does. So I had more in there. I said the moisture barrier is a membrane used to resist migration of liquid water through a floor, wall, or roof. So a moisture barrier is what really a roofing membrane would be. A roofing, shingle roofing, any kind of roofing material is a moisture barrier. That's what you really want there. Whereas a vapor retarder should allow a certain amount of moisture to dry out through it, to diffuse out through the surface. And so when we're talking about house wrap is a vapor retarder. So some people will call it a vapor barrier, and that's a misnaming of the term. It's less accurate. And so that's not really a correct terminology. And so I want you to know that well so that you can understand, because people will correct you sometimes on that. So yes, as a teacher, I'm correcting you maybe, but I mean, so remember, it's a vapor retarder, even sometimes when I accidentally call it a vapor barrier, because I grew up calling it that, and I've had to change and try to change my language. And then the third top, so that's dealing with resisting the diffusion of vapor. So you want it to water to condense on the surface of the house wrap, or on the barrier on the inside of the house, on the insulation. If you got fiberglass batting on the inside of your house, you've got a craft paper typically on there. And that's a vapor retarder also, to keep moisture from condensing inside the wall, inside the insulation. You want it to instead condense on the surface of the wall. And if it gets past there, on the surface of that craft paper instead. But if the moisture does get in, you got to give the wall system a way for the moisture to evaporate out, to diffuse out. And so that's why we call it a vapor retarder. It needs to be somewhat of a barrier, but not enough to keep the moisture festering in there. And then the last one down here is air barrier. It says a material that reduces air leakage through a building. So that's also house wrap does this, in that it's supposed to lock up in a way to keep air from blowing through the building, blowing through the wall assembly, because that wouldn't be good. If you got a good strong wind blowing, it's going to start pushing air through that wall. And so as much as you can, you want to make an air barrier and still have it as a vapor retarder. So that's a house wrap has 2 roles, and that's why it's woven material instead of a solid sheet of plastic or something. You want it to lock up like a solid sheet of plastic, but still allow moisture to diffuse out. So as you look at these terms, whatever I'm asking a question of, you look at the word. It's a barrier. If it's if it has the word barrier in it, then that's something that's actually meant to keep something completely out. So keeps moisture. Moisture means water. It means liquid water. So moisture barrier is liquid water. Vapor barrier, you're talking about a gaseous water that's evaporated into the air. It retards. And so it's not a barrier per se. And then air barrier, well, it's a barrier, so it's stopping air, locking and keeping air from blowing through that assembly. So just if you look at the individual words, you can kind of figure it out from this. Okay, so now this page is a little more heady, and I guess maybe I got more information on this page particularly, but when we're talking about a vapor retarder here on this other page, this is where we're kind of getting into some language about that. A vapor retarder should be somewhat permeable, meaning that vapor can permeate through it, can flow through it, can evaporate out through it. So we talk about its perm rating, vapor permeance. Okay, it's all kind of the part of the same root word. And so, yeah, I got a bunch of things talking about a perm rating greater than 1 grain per hour, foot squared per inch mercury is not acceptable. Okay, so if it's going to be a vapor, as a vapor retarder, it's got to have a number less than 1, or 1 or less, I guess, on a table. of this measurement of permeability. So there's a numbering system here, but I'm not going to directly ask you that. I've just kind of putting that as in preamble. So vapor permeance is the measure of the ease with which water vapor can diffuse through a material. So in that case, we can talk about, for instance, gloss paint. When you paint a surface, that makes the material less permeable. So that would be a stronger vapor retarder than flat paint. Gloss paint is more of a barrier. It's not a barrier, but a vapor. And so literally that can make a difference with whether you're a flat paint or gloss paint will have a different vapor permeance. So we're talking about the measure of how easy it is for water to pass through, to diffuse through, to evaporate out through over time. That's what we're looking at here. Anyway, so when we talk about vapor pressure, a measure of the pressure exerted by water molecules in a gaseous state, generally higher with the higher relative humidity and higher air temperature. So that's another aspect in here. So I'll circle back to this because it's a heady page, but there really is, it's less trouble. If you just understand what these words are, you're not going to have trouble with the questions I would ask. Okay, this is a better page for being more common sense. We talk about thermal bridging compared to a thermal bridge compared to a thermal break. And then we also talk about comparing R value to U factors. So these are two different topics, sort of. They're related. But so a thermal bridge means that temperature can conduct through a material. You think about the bridge allows you to pass from one side or the other, across the creek or whatever. Well, a thermal bridge allows temperature to cross over through a wall system, for instance, through a window system. If you've got aluminum framed windows, the old-fashioned aluminum or steel framed windows for that matter, even more so, the temperature is going to conduct right through there. You got a thermal bridge there. It's not an insulator. It's the opposite. So they do make an aluminum window, a high-grade aluminum window, where you got two pieces of aluminum, one on the outside and on the inside, because aluminum is a very durable surface. It's going to last longer than pretty much any other kind of window frame material you can make or build. Way better than vinyl, for instance. Vinyl is going to deteriorate over time. It's a fairly short-term material with the sun eating it up. But so the thermal break, they do is they actually install the window and some plastic and put some aluminum on each side. So there's actually a break between one piece of aluminum and the other with a piece of insulating material with the plastic. So that would be an example where you're stopping the conducting of temperature through that system, through that aluminum frame. So the idea of you can frame a wall where you've got a bunch of studs in the wall. Well, the studs are going to be, an insulator to a degree, but nowhere near as good an insulator as the wood. As the insulation, the fiberglass batting or the styrofoam that you might have in the wall or whatever, the foam that you have in the wall. So to some degree, you're allowing temperature to migrate through the wood. Because if you put a lot of wood in there, if you got a whole bunch of wood framing, like the traditional framing around a window has been a whole bunch of wood around a window with a header and everything, you get cold windows because of that. Cold framing, not just the windows, but the framing around it. Because of that, you have a thermal bridge. And it's even worse if you got metal studs for your framing. Well, the temperature is going to conduct right through that wall at every one of those studs, because steel is not an insulator at all. It's going to conduct very, very well. So you get the difference. Bridge, you're talking about thermal, that's temperature. Thermal bridge, that means temperature can migrate through easily. Thermal break, temperature cannot, because you've interrupted it by how you've built the wall. So you could build a wall with two 2x4 frame walls spaced apart a few inches and put a bunch of insulation in that wall. So there's no actual wood except a strip of plywood at the top and the bottom of that wall frame, allowing moisture to conduct through that wall. It's a very good thermal break. Okay, down to the last two topics on this page, 2 bullets, R value and U factor. R value is what we use to measure insulation, how good of an insulator you have. So the higher the number for R value, the better the insulator. It's a number. It's a numerical measure, as they say. It's a number. So an R value of 13, an R value of 11 is pretty common for fiberglass batting in a 2x4 frame wall. That's about all you can do with fiberglass batting. If you go with spray foam, you might be able to get to R19 with that in that same space because you're using a better insulator that has a higher R value. So the higher the number, the better the insulator. R values are additive, so you should remember that you can add them together. We had that kind of as a math question at some point, I think for exam 2, where you were adding a sheet of foam sheeting to the outside of the building, or maybe a couple of them, and able to add the R value of the 2x4 frame wall with the fiberglass batting. Maybe that had R11 or 12 or something, and then you had an R value per sheet to add, and they can just be added up. But anyways, the thing is that windows do not have good insulating numbers at all. They're horrible. The very best windows you can buy are rated at R value of 5, whereas a pretty lousy wall system might be an R value of 11 or 13. Pretty common and plain, vanilla, boring, and lousy, not particularly remarkable. It still could be, 2 or 3 times, it could be several times better than the windows in your house. So the windows are a horrible, even the very best windows you can buy are horrible as far as insulated dye. So they don't like to talk about the R value. So instead they use a U factor, which is the reciprocal of the R value. So whereas R value, the better insulator, is a bigger number, with a U factor, the one with a better insulation or better insulator is for U factor is a smaller number, because in other words, it's going the other direction. So the smaller the number, the better it is at insulating, at energy efficiency and stuff. So one is the reciprocal of the other. So I have that written there, the last part of the phrase in both of those things. The mathematical reciprocal of the U factor is the R value, or the mathematical reciprocal of the R value is the U factor. So and what does that mean? It's 1 over the number. And so if I have an R value of 10, for instance, I pick that number because it's a easy number to do in my head. 1 over 10 would be the U factor, which would be 0.1. So I made it easy on myself, fairly easy anyway. So, so basically, and then U factor, if I go take 1 over if I got the number 0.1, 0.1, if I go 1 divided by 0.1, I'm going to get 10 if you do it on your calculator. So you're just reversing the process. So 1 over the number, that's what reciprocal means. It's the inverse is another word that sometimes I use. So depending which way, if you've ever heard of that terminology, one way or the other, reciprocal or inverse mean the same thing as far as mathematically speaking anyways. So remember that. But we generally use U factors for windows and R values for everything else. Residential electrical services. We're finally getting to the last topic where we're dealing with electrical and HVAC. So the first part is electrical. And so you're going to have a picture just like this on your learning outcomes exam, except that instead of all these words you see surrounding it, you're going to have the letters A, B, C, D, E, F, G, maybe something like that, pointing. And I'll be asking you things about these things. So in here, this is a service panel where the electricity for your house would come from above. Now, if it was coming from below, if you had underground electrical, then those same 3 wires that you see at the top coming through a service entrance conduit or something would be coming from below. Now, before it gets here, it's from, it comes from the roof, it's got to go through a meter so that the power company can sell you some charge for the electricity. But otherwise, we're not showing that here. But otherwise, you've got 3 wires from the power pole or from underground coming into this box. The 2 black ones that you see at the top, those are the hot wires. Each one of them is going to be generally having about 120 volts or so, depending on the quality of your electricity coming to your house. 120 volts a piece. And if you were to grab a hold of both those wires, you'd experience 240 volts. So you don't want to do that. And if you're just grabbing hold of the other wire that's got little stripes on it or something, that's the neutral wire. It's normally white. And if you were grabbing a hold of that white wire and one of the black wires, you'd experience 120 volts. Well, that's not what you're going to want to do. You take a meter and, a multimeter, and you test the voltage. That's what you could do instead. But anyways, that's where the power comes in the building. So that's the service conductors coming into the house. The main breaker you see down below that, this breaker could have been outside of this box. And in best practice is it should be outside the box so you can shut off power to the entire box would be the better way. But anyways, main breaker is there. And then all these individual breakers down here, half of them are getting power from one of those black wires, and the other half of those breakers are getting power from the other half. And when you have a double wide breaker, it is giving you're getting power from both sides in order to run something like a 200, like something that needs 240 volts, like like a electrical cooktop or an oven or an electric dryer or your central air conditioner. Those are the kind of things that would need both wires. But otherwise, you're getting one or the other wire to power things like your computer and lights in the house and TV and those kind of things. So that's looking at the power side of things. And so those wires that are coming from each individual circuit breaker are the hot wires going out to wherever they're powering something. Meanwhile, that white wire that was striped up at the top that was coming from the power pole is connecting to a bus bar over on the upper right hand corner in this particular picture here. And all the neutral and the ground wires get hooked up to that bus bar, and they go out to everywhere they need to go in the house. So those are neutral and ground wires. Those are return paths for power. So then white wires are what we call neutral wires. They are supposed to be the official proper return path for power. And the green wires, those are ground wires. They're supposed to be your backup or alternate path only for emergency use path for returning power back in order to trip a breaker properly, to make sure the breakers really do trip instead of sit there electrocuting or burning the house down or something. So you have those systems. And so then you got to have a backup return path. In case something happens to the power pole neutral wire, you still need that return power to work. So we have the grounding conductor that comes out of the box. You see way over on the right-hand side, you might be able to see my cursor swirling around it, where it's got a green wire taking a little bend down, and then it's got a longer line and a little bit shorter line, a little bit shorter line. That's the symbol for grounding. And so this means you would have an 8-foot grounding rod driven into the ground outside this service panel with a wire coming from this panel, this wire here, and it would be connected to that grounding cable, that grounding post, really, that's driven into the ground. This is our official grounding, known ground, established ground, and everything. So with that, I think you know enough to answer anything I would ask you about. But if I might ask you, okay, where's the grounding, the grounding electrode conductor? Is going to the main grounding post or grounding rod that's driven into the ground. Well, then you can see that, where I have over here, where I've got grounding electrode conductor with the arrow pointing it, that's what we would be looking at. If I'm asking you where the two hot wires are that come from the ground, well, you'll see that I've got it written over here on the upper left-hand corner. It says ungrounded conductors, service 120/240 volt hot wires. So these are the kinds of things that I could ask here, and not much else. Neutral wire. Which one is the neutral wire coming from the power company? Well, you see that up at the very top right-hand side, it says neutral grounded conductor. Well, it's grounded because it's connected to that bus bar that other grounding conductor is connected to. So that's why you say it's grounded. It's also grounded back to the power company, but that's a different matter. Okay, so that's where I can ask it. I can ask it where it's looking more like this almost, maybe not quite this bad, but where you're looking at it, but I'm just got some, it won't be cropped this much, but it will be cropped enough so that you are seeing just the box and with a bunch of letters with the arrows pointing to stuff. Okay, let me skip along here. And then they've got the last section here today is about about air conditioning. So as a Canadian who didn't really care much about air conditioning until I moved to the South here, where I suddenly learned its value here. It's kind of crazy that here I'm describing how an air conditioning system works here, but this is a central air conditioning that you have in your house. If you had a window unit, well, that's got all of this stuff, the inside and the outside stuff, all combined together as a compact unit. So of course, it's still going to be easier to understand this unit than that one because it's all so compressed together in a window unit or a portable unit of some kind. So, with this process here, we've got refrigerant that is pumped up into the house, into the coils. It's in the coils, outside coils, inside coils. We got two sets of coils. And in this particular drawing, it's showing the coils, or they're showing the inside unit in a basement. And yes, if you had a basement, that would be a good place to put it. But a lot of our systems are in attics or in a hallway closet because we don't have basements in Louisiana. So that's a difference here. But otherwise, you're looking at the outside unit. You've got a compressor that compresses the refrigerant, and it has condenser coils that allows the refrigerant to cool off and condense back into a liquid. So, because the refrigerant is supposed to be a liquid before it leaves this unit, and then it's pushed up as a liquid up into the house, into your attic or into your closet, wherever you've got the evaporator coil. So the condenser unit with the condenser coils that has a compressor there too, that's outside. And then it pushes this refrigerant as a liquid up to your attic or wherever it's going, wherever you got it in the house, to the evaporator coils. And it actually goes through something they're not really showing here, but it goes through what do they call oh gosh. Let me go to the next page because the words on there. It goes through let's still not call that. It's not on there. How come I can't remember? It's a expansion valve. Okay, so expansion valve here. So just before it goes through the evaporator coil, so that way it's basically has it's like a tin can space that the liquid goes into. That's allowed to, but it goes through a pinhole before it goes into that space. So it expands into a gaseous state by going through a pinhole, and so that becomes the rate at which it can be pushed through. As it goes through a liquid and it comes into an open space, it's going to turn into a gas. When it does that, it gets very cold. Pressure and temperature are directly related to each other. So as you decrease the pressure, you're going to drop the temperature, and so it's a way to exchange heat and temperature. So out of that, then you get this gaseous evaporated refrigerant that's in these coils, these evaporator coils, and it's cold. And so it makes the coils very cold. And so then we can push air through it. And that air is going to then get cold, and you can push it through the house and cool off the house. But in the process of doing that, you're warming up the refrigerant. And so that refrigerant gets warmer because you cooled off the air. That means you're warming up the refrigerant. And so the refrigerant, as it leaves the coil and goes back to the outside unit where the compressor and the condenser are at, the refrigerant is turning into, it's warmer. And so that warmer material is in a bigger tube, and that bigger tube comes back and then is going to get cooled off in the condenser coils, and it's going to get compressed into a liquid for good measure, and then pushed back up into the attic. And so this is how you have this cycle, how the system works. So you're going to see not this nice pretty picture, but this picture here. I guess because it's simpler to put on a screen, but it's also two-dimensional. So again, you've got the outside unit with the coils, and you got the inside unit with its coils. The outside unit, those are condenser coils. The inside unit, you got evaporator coils. So if I was to ask you, where in this picture does the refrigerant, sometimes you might call it Freon. In the old days, it was Freon. We don't call it Freon anymore. The stuff that we use that was a brand name of particular stuff that's all kind of obsolete now. So refrigerant is the right term. Where is the refrigerant converted into a gaseous state? It's going to be up here where the evaporator coils are at. So you'll have a letter there somewhere next to it to point to. And then, of course, it goes back and where is the refrigerant, where is the refrigerant get cooled back off again? Well, it's going to be out here at the condenser unit. Or maybe a better question that I might ask is, where is the refrigerant turned back into a liquid? And that's going to be out here at the evaporator coils and the compressor area here, in that unit. That's where that happens. Oh, and another question I can ask is, where does the heat ultimately go? Well, yeah, we know the heat is in the refrigerant when it comes back out to the compressor unit, but there's a fan right there that is sucking air through those coils in order to cool it off. And therefore, the fan in most of these units is pushing straight upward, and it's just like this one does. So the fan is blowing air straight up above this condenser compressor unit, this outside unit. And so where is the heat ultimately going? It's going into the air above this unit, above this outside unit, the compressor condenser unit. And so I can have a letter of some kind up there, letter A, B, C, whatever, sitting there. So that's where it ultimately goes, where the word fan is at, above that compressor condenser unit. So just remember those basic questions or basic the logic of all this, and you're not going to have trouble with the questions. I don't think. Okay, so just a little bit more detail here for the fun of it. At a commercial level, they don't have a model like this. Instead, they have what we call chillers. So you see this big blue turquoisey looking thing that's in a circle form like a locomotive almost. That's what most chillers look like. Big cylinder on its side. And and then outside unit is called cooling towers. They look like what you see in the middle picture. So the middle picture is showing you cooling towers. So let me show you how they're used. Okay, so in this model here, you've got the chiller, the big cylindrical thing. And you see that in the middle of the drawing here. So there is a refrigerant going on in here too, just like in the other unit. And it's going to cool down, not air. The refrigerant is going to be used to cool off water that we call chill water. And the chill water goes through the chiller and it gets refrigerated. It gets cooled off, very cold. And by that, it's probably about 55 degrees, maybe. It's in the 50s. And it's pumped with a pump to buildings. So our BRCC campus is like that. LSU has a whole bunch of big chillers and various sizes. And they got a whole network of insulated pipe that's pumping chilled water to all the buildings, and they run through an air handler, a bunch of coils, so that they can cool off the buildings. And so then when that chilled water leaves that air handler, it's warmer. It might have gained 5 degrees or 7 degrees or something. So it might be maybe almost 60 degrees. And it goes back to the chiller and gets refrigerated and comes back. And so it's going through insulated pipe and it's being pumped around in a big wheel, a big cycle. Well, as you can imagine, just like in the other case, the refrigerant gets warmed up in the process of cooling off the water. So we got to cool off the refrigerant. And so that's what this condenser water does. In the lighter blue pipe that's still insulated, but it's running may not be insulated pipe there. Doesn't have to be. But it's running out to a cooling tower outside where where the water is actually run down a series of ladders in open air to cool off the condenser water, which could be significantly warmer than the chilled water, but it's still cooling off the refrigerant. It might be cooling the refrigerant down to 70 degrees or something, 70 or 80 degrees. And so out of the process, then that's going around. And so you're cooling off the condenser water so you can go back and cool off the refrigerant water. So they just have two different water systems, and it's all treated water generally, so that, it's running basically kind of like with coolant, kind of like your radiator in your car would have antifreeze. It would have some kind of treated water in there. Anyways, that's how they work. So in the end, normally that's the last thing I talk about. So I say that's all, folks, here. But this is all there is to the learning outcomes test. So just understand that there's about 27 questions, 25 to 27 questions. I can't remember which now. One of the tests is a little different than in learning outcomes in safety is a simpler test, but there are some topics in there that we've been just covering lately that are critical stuff that we need to go through. So if you're in my safety class, I'm going to be going through that soon too. But we have next week, with Thanksgiving week, there are classes on Monday and Tuesday, but there are no classes on Wednesday, Thursday, Friday, Saturday, all the way. So, through Thanksgiving. So within our materials and methods class, if you're listening to this, if you've been coming to or participating in my face-to-face class, there is no class on Wednesday. So you can come there if you want. You'll be all by yourself, but yeah, I'll definitely be there on Monday. If anybody is that's listening here is in my online class, there's only a one or two or three people that show up for that face-to-face class these days, because I've got a teleconferencing system for them too. So some of them are, so if you particularly wanted to come for some face-to-face time for math or some of the math problems and stuff, you're welcome to join us at 1:30 to 2:45 in room 116 in the Cypress building. So Cypress 116, starting at 1:30 on Mondays and Wednesdays. So it's up to you. I should have said something about that earlier, because it's been basically me and another guy or two or three at best in the afternoons on that. And I usually have some people that are in the teleconferencing system. The problem with the teleconferencing system is it only allows 24 people to be in there. So it's hard for me to go and invite people from the online class to be in that. But I possibly could if needed. I still have a little bit of space in there for that, because not everybody is participating with that either. Okay, so with that, let's see. I would just maybe summarize a little bit before. I don't want to, in this, let's see, we're looking at the time. I'm going to go back and make remake the video from last week that's not working. And I'll post that and announce that. And that's dealing with the week 12 material. And then with the week 13, we really can continue with that into the week after Thanksgiving too. So there's some of that that we can go through. And I'll make another video within all that too. But this, let me go and just share the page where this of Canvas again one more time. So here we are in Canvas. And so again, after exam number 3, we had week 12, and that's the material that I need to go through again. But it's basically dealing with structural steel. That's the big chapter in that week. There's a much shorter chapter dealing with light gauge steel framing. So that's framing with metal studs. So there's more to it than you might think, but it's going to be a relatively short chapter. There'll be twice as many questions coming out of chapter 11 than you'll find out of chapter 12. But half the questions for exam 4, which is our final exam officially, that's what we'll be using for our final exam, is only dealing with chapters 11, 12, and 16. But half those questions will come out of chapter 16, which is dealing with roofing. So I've got it as chapter 16A. So the first half dealing with low slope roofing, where we're dealing with very gently sloped roofs that you can't use shingles on, And so by definition, a low slope roof is a 212 slope or less. And anything steeper than that is definitely considered a steep slope roof. So the steep slope roof, chapter 16B, that's where we'll be dealing with shingles, whether they're wood shingles, composition shingles of fiberglass asphalt shingles would be the most common thing. Could be shakes, of wooden shakes possibly, but it's also tiles, terracotta, ceramic, clay tiles, all of those things, I guess, if they're used for roofing. Concrete tiles, slate roofing, Now, the one membrane, so we're talking really between slow slope and steep slope, the difference is basically because of how steep it is. When it's a gentle slope, you can't use shingles because the water will back up underneath the shingles. So that's why we break it down into two different kinds. So in there'll also be some math calculations, some roofing calculations, because I want you to be able to know how to calculate out a simple roof that is a low slope roof or a steep slope roof. And so I'll be doing some serious math to show you how that works. You're going to have basically a question where you're calculating how much a low slope roof, and you'll be calculating a steep slope roof. Well, a low slope roof, you can treat the roof like it's perfectly flat. It won't be quite that way, but for estimating purposes, it'll be very accurate about what you need. And so you just treat the roof like it's perfectly level and figure out how many square feet you have on it. Whereas for a steep slope roof, you need more roofing surface on there as you go up. The steeper the roof, the more roofing surface that you have to have roofing materials for. And so it all has to do with calculating, depending on what that roof slope is, how much more roofing material you need there compared to the low slope roof. Even though we're generally dealing with very different materials, there is one material in roofing that is not like the others, and it's sheet metal. A sheet metal roofing material can be the roofing deck itself, the deck material that's supporting the roofing, and it's the roofing also. It's the roofing and the deck. So there's money to be saved. It's the cheapest system you can have for a roof is to have sheet metal. I shouldn't say it that way. It's the most economical kind of roofing material because the roofing material can be the roof deck and the roofing material. But the second thing I was ready to point out actually first, but I'll get to it now second, is that sheet metal is the only material that I ever can think of that works both for a low slope roof or a very flat roof or a gently sloped roof, and it works for steep roofs. So it's the only material that crosses all boundaries, could be used for both. Now, sheet metal roofs, some homeowners organizations or HOAs or whatever you want to call them, associations, homeowners associations, they don't allow you to have sheet metal roofs because it kind of like in some people's minds, in some ways, they can think of it as being kind of like a too much like a trailer court kind of a thing. I don't know, but it just depends on the sensibilities. But of course, there's some very nice sheet metal roofs out there, so it's not completely true. But there are rules, and you may not be able to have a sheet metal roof on your house in certain neighborhoods. Let's put it that way. But but it is magical in the sense that you've got a roof deck that is also the roofing material. Now, if you're retrofitting a sheet metal roof onto an existing roof, so you're not going to take the roof deck away in the roofing. You're just going to build over top of it. So that wouldn't be an argument for that. But if it's new construction or if it's whatever. Anyway, so the point here is that we're going to have to go through a lot of details on the roofing here, but I think that's a discussion for another time. I think it would be best to stop this one right now, and we'll kind of move on from there. I'll definitely, I promise I'll get those other recordings to you, and then we'll be continuing on. We'll definitely have even the week after Thanksgiving, we're going to have another Zoom session here like this to kind of review everything else that we got going on. But you got several things coming right now to focus on, and that is that, yes, this learning outcomes test, you can go through this presentation a couple more times. The sooner you do it after you watch this video, the better. Or if you're here presently, particularly, go through it again to kind of review it, to refresh your memory on everything I just talked about here. And then you'll be ready for that test that opens up next week. Did I figure out when? I think learning outcomes, it opens up on 23rd, I said. Wow, that's that's the Wednesday. So it'll open up then. Doesn't mean you have to do it then. It'll be open all the way till the following Wednesday, which is the Wednesday after we get back. But that's why I wanted to go through that today, and we'll go through, still have, 2 weeks left, basically, including Thanksgiving, to kind of be ready for the final exam, which is exam number 4. It's not comprehensive. The only thing that's kind of comprehensive is this learning outcomes test that we just went through today. However, let me go and try to figure out how many test questions there are here right off the bat. While you're in here, I can look. You can see those pictures in there. Anyways, with it's not telling me here in this version. I know where it would tell it to me. It would be under quizzes, I think. Going to that section. I think I was kind of seeing it, but I was trying to figure out just to be sure. If I'm going to tell you how many questions there are, I want to be right. 25. Okay, so it's the safety course that has the 27 questions or something like that. So a couple of extra questions. So yeah, 25. There's 5 per topic. So that gives you the idea of what you're dealing with. So it's not as involved as a test compared to our other tests that have had 50 questions, even though it's worth just as much. It's worth 10% of your grade as the other exams. So the problem with less questions is that each question counts for more. So each question counts for 4% of your grade. So, that's why you want to be careful with it. It uses Proctorio just like the other tests. So I'm going to go and tweak those Proctorio settings to a little bit, because I think it's been a little bit problematic for a few people. So I'll see if I can fix a few settings on that. Okay, so with that, I'm definitely need to call it a day, and that I appreciate you all being here. And I see you typed your names in the chat box. Great, so I can give you some points for being here too. So I'll hang on, and I'm going to turn off the recording and hang on here in case anybody has any questions or concerns. So I'm turning off the